before I get to that, I want to point out to you guys that on the My Notre Dame page, I have the agenda for the rest of the semester up. So we're going to try to finish out chapter 4 here. And then I'll talk about exam format a little bit in the future once I kind of have a better picture of exactly what how I'm going to do that. But I'll give you guys plenty of heads up on that and get you some stuff to start prepping here sooner rather than later. But I just want to give you a heads up that that's going. My kind of thought right now was keeping like this in mind. So this is like the scoring ranges from last year's AP exam and kind of how it maps out to a score. My initial thoughts for the final would be giving you something where there's like 100 points of questions and you need to complete 70 points worth for 100%. So it'd be something like you have some freedom, you can work on some stuff, you don't necessarily have to finish everything. Like that's kind of the thought process where I was at. So it's a little less of a concern for me making sure the length is right, because if it's too long, that's okay, because it's only out of, you don't have to finish everything to get 100%. In fact, you only have to finish really 70% of it to get 100%. That's initially kind of my thoughts. I'll give you some more details once I get a little bit closer to that mapped out, Mackenzie.
So, 2 questions.
Mm-hmm.
When you say finish, does that mean you have to get it right also, or you just have to complete it?
So like there's like 100 points on the test. You need to just earn 70 points of that to get 100%. Like the thing would be, the way I look at this, it's like, okay, there's 108 points on the AP exam. A 70 is a 5, like 100%.
Okay.
So that's kind of what my thought process was, thinking about how to put a final exam together that's going to be lengthwise feasible, and I can still put on like everything I'd like to put in there.
Okay. And then after, like the scores after that, like 4, 3, 2, what do you get if you got it?
Well, I would just grade it out of 70 points.
Oh, okay.
Like there's 100 points on there. It's graded out of 70.
Okay.
Anything over 70 is still 100%. And just like if you got a 65, then you got 65 out of 70, whatever that converts out to as a percentage. You know what I mean? That's kind of the way I was thinking.
Okay.
I'll give you some more details when we get a little bit closer and I have more of the thing done. I've just started drafting and putting questions together. Taylor?
How much is the final word? Like how much
15.
15.
Yeah, 15. All math finals are now 15%. Anyways, I put all this up on My Notre Dame a long time ago, but like this is the score distribution from last year's AP, or maybe it was 2 years ago. Whatever the latest data was available when I looked for it. Oh, it's the last 3 years, 2021, 22, or 21, 20, and 19. So, and then this is the distribution or whatever, point distribution. Anyways, everybody cool there? Okay. I know you guys were asking about exam format before break, and I thought a little bit about it, and I think that's probably where we're going to land, but I still need to spend some time getting questions together and thinking about the format a little bit more. Well,
will we have chapter 4 just in the final, or will the final be?
The final will just cover chapter 4 material. Yeah, there's no time to do another part to chapter 4, or a chapter 4 test beforehand. Yeah, Taylor. Oh, okay, no problem. So let's start questions. I think you guys should have, or we had assigned up through homework from 4.1, 4.2, and 4.4. So if you guys have any questions from those things, I'm happy to take a couple of those before we start 4.3 stuff today. Victoria? 4.428. Okay. So first thing we need to do is check to see if this is actually in the indeterminate form, right? So if I plug in 0, sine of 0 is?
1.
It's 0. So I have 0 on top. And tan of 0 is 0. So I have 0 over 0. So that is in the indeterminate form. So L'Hopital's rule should apply. How do we do L'Hopital's rule then? We do the derivative of the top over the derivative of the bottom. And Mr. Kulik made a mistake here. What did he do wrong? Yeah, I didn't write the limit. Okay. So if I do this again, cosine of 0 is 1. So I have 1 minus 1 on top, so that's 0 on top. Secant squared of 0 is 1, so I have 1 minus 1 on bottom. Still indeterminate, right? Okay. What do I do? L'Hopital again. So derivative of negative cosine is?
Wait, I have a question.
Yeah.
Like, what is, like, well, how do you know that secant squared is 0 is 1?
Well, cosine of 0 is 1, right?
Yeah.
And secant is the reciprocal. So the reciprocal of 1 is still 1. And 1 squared is just 1 still. So because cosine was 1, I knew secant was 1, and 1 squared is still just
And,
1.
like, is it, but, like, for 1 minus secant squared, isn't there, like, like, that equation? Is there something that, like, you put in?
Oh, you want to use a trig identity there? You could potentially do that, and you might be able to get around the having to do L'Hopital again. That's possible. I would probably just keep going because the L'Hopital is not bad, but that's worth considering. That's absolutely a case. What is secant squared the same as? That's like 1 plus, is it cotangent? Tangent squared. Okay. I should know this. We're doing this already in, or doing this right now in trigonometry, so I should have all those fresh in my mind, but, you know. All right. So we do L'Hopital again. Derivative of 1 is 0. Derivative of cosine is negative sine. Derivative of secant squared. That's a chain rule problem, right? So derivative of the outside is 2 secant x, and then times, what's the derivative of secant? That is secant times tangent, right? Okay. So what do we have here? We have just do a little simplification before we try to do this. So I have sine x on top. And then I have 2 secant squared times tangent on bottom. And this, we might be able to algebra up a little bit to make life work out for us. Again, if I look, sine of 0 is 0, tangent of 0 is 0, so I still am in an indeterminate form, right, Victoria?
Yeah, why is that negative 2?
Sorry, should be. Thank you. But methinks at this point, there's some simplifying that can happen here. So I'm going to try to do some trig identity to trig this up a little bit. And see if I can get enough stuff to cancel out to where I don't have to try to L'Hopital this again. Since this is all just a single fraction now, instead of having any addition or subtraction going on. So I have sine divided by tangent is the same thing as like sine times the reciprocal of tangent. And we okay with that? Oh, yes, Mia? I mean, like assuming it's a calculator question, you could do that. If it's a non-calculator question, I mean, the way it was currently written here, this is still 0 over 0 if you do a direct sum, right? You know, like, I'm just guessing that you can simplify this enough to where, actually I can see that I can simplify it enough that things will work out kind of nicely for us. And then secant is the same as the reciprocal of cosine, right? Everybody's okay with that? So what I really have here, and 1 over tangent is the same as cotangent, right? So I can do this to get no fraction at all. And that should be really enough, right? Well, the only issue is that, I guess, cotangent is undefined at 0, which is not helpful, but what's cotangent the same as? Cosine over sine, right? And that's now direct sub cosine of 0 is 1. So we're good. We're just negative 1/2. Is that okay, Victoria?
Yeah, wait, so cosine of 0, 1, so to the third doesn't matter.
So just 1 to the third, which is still just 1, right? No big deal. Yep, exactly right. Serge?
Can you remember? 35.
4.1?
Yeah.
Sure. And you said 35 or 45?
35.
Okay. Do. All right. So this is asking for the critical numbers for the function. Reminder that the critical numbers are the place where the derivative is either undefined or equal to 0. Now, I should here check at least quickly what the domain of the original function is, because if it's undefined in f, if it's undefined in f prime, it doesn't matter, right? Those don't count as critical values. I recognize that my function is going to be, or domain is going to be all real numbers except where the denominator is equal to 0. That doesn't factor, so I would be stuck using the quadratic formula. But if I do that, I notice that I'm going to get a negative number underneath my radical. And if it's equal to 0 for an imaginary solution or imaginary number, it doesn't really count as a whole in the domain. So the domain for f is just all real numbers here. So we're good. Anywhere where the derivative is undefined will be an issue. So let's calculate the derivative then. To do that, what do I have to do? Quotient rule. Okay. So we have the derivative of, is it the top or bottom? What do we start with? The bottom, okay. Times the top minus times the bottom all over the bottom squared. Now that's lovely because I know that since this is the same denominator, the domain here is going to be all real numbers. So there's no critical values for where the derivative is failing to exist. Awesome. So all I really need to worry about is when this piece is equal to 0. Cool with that? All right, so let's FOIL this stuff out. So 2y squared minus 2y minus 1y is minus 3y plus 1. And then we have a minus y squared plus y minus 1. So that's going to give me y squared minus 2y equal to 0. I'll solve this by factoring. So my critical values there should be 0 and 2. And we're done. Let's go back and double check the solution manual. I guess this was an odd one. You guys would know if I did this wrong or not, I suppose. Yeah. Yep, 0 and 2. Mia, is that a hand?
Yes. Can you please do 37 on over 1?
37? Okay. Sure. So same directions here. We're just looking for critical values. Okay. I noticed that these are the same as fourth roots, right? Since they're to the denominator and the exponent is 4. I know there the domain then is going to be 0 to positive infinity, right? Everybody's cool with y? Can't take an even root of a negative number, right? That's all. Same rule as with a square root. So the derivative then is going to be 3/4 t to the negative 1/4 minus 2 times 1/4 t to the negative 3/4. Everybody happy there? So let's just kind of clean that up maybe a little bit. We'll call this 3/4 t to the 1/4 minus 1/2 t to the 3/4. So I can see right away that the derivative doesn't exist when t is equal to 0, because that'll give me a 0 denominator in both fractions. I really only need a 0 denominator in one of the fractions to be for the derivative fail to exist, but it happens in both fractions. Good with that, Mia? Okay. And then we have to then check where the derivative is equal to 0. So let's do that. Oops, that's a 1/4. Anybody with any ideas, clever ideas on how to do that, to solve this? Yuck. Let's do this. Multiply both sides by t to the 3/4. That'll give me 3/4 times t to what power? Two-fourths, which reduces down to 1/2. When I distribute here, I get what? Negative 1/2, t to what power? T to the 0, right? Which is just 1, so that's great. Boy, that makes life a heck of a lot easier now with the variable just in one spot, doesn't it? Okay. So we'll add 1 to both sides and then multiply by the 3/4. So t is then going to be 4/9. And then 0 should be my two values. And that is correct, looking at the answers. Is that cool? So again, this trick of just clearing the fraction out of there, like massively easier than making a common denominator. That would not be wrong. It will still work. It'll be messy though, I think. Did they get really bad? Is that what you tried to do? And it just got messy and probably made some silly mistake and then we couldn't get the right answer? Yeah. In general, if I have a situation like that where I have x's in the denominator, I'm clearing fractions to solve. Or variable in the denominator, I should say.
So I should always use that trick.
Yeah, I think it makes the solving. It's never going to be the hardest way to do the solving. It's almost always going to be the easiest way to deal with it. Just getting rid of the fractions. It's really easy to make silly algebra mistakes with fractions, and if you just don't have them, there's no mistakes to make, which is pretty nice. Serge, what's up?
How did you get t equals 0?
Oh, well, if I look at this, where is this function undefined? Well, when the fractions are over 0, that happens only when t is equal to 0, right? It doesn't have to be both fractions either. If you have one fraction that has a denominator of 0, that's enough to make the whole thing undefined. Taylor.
So when you're finding the critical values,
Mm-hmm.
you're just kind of setting the equation equal to 0.
The derivative.
The derivative equal to 0.
But you have to check where it's undefined also.
Okay. So is that where you put like the t is equal to 0?
Yeah, so this was me checking for where it's undefined. The derivative doesn't exist there. And then I'm checking after that for where the derivative is equal to 0.
Okay.
So those are the two places I need to check for critical values. All right.
So is 0 always that way? Right, no.
Okay. Anybody else here? Okay, cool. We can always come back and deal with more stuff from here if you're still getting caught up on things. That's okay. .3 is what we're going to talk about today. And what 4.3 is going to talk about is it's going to relate information about the derivative with the shape of the function. So if we know stuff about f prime, what can we say about the shape of the graph of f? So we're going to start with what we'll call the first derivative test. And that just says that if f prime is positive on some interval, then f is increasing on that interval. And if f prime is negative on that interval, then f is decreasing on the interval. When I draw a picture, what does increasing look like? And what does decreasing look like? So it means that just if you have like a graph and you have a little man walking along the top of your curve, increasing is that little man's walking uphill as you go from left to right. And, you know, you're going downhill if you're going from left to right. That's decreasing. That's all we're saying, which makes sense, right? Because the derivative is a proxy for slope. If the slope is positive everywhere, it should be going uphill. If the slope is negative everywhere, it should be going downhill. So let's prove this real quick, because it's a nice one, because we take advantage of a couple of other tools that we've developed recently. So what we want to do is we want to start and let so we're just going to pick these guys to be real numbers in the domain of f. And we're going to say for without loss of generality that x1 comes before x2 on the number line. Okay. So since we know f prime of x is greater than 0, that f prime is differentiable at x1 and x2. And what can we say then about that? Well, really, we can probably, here we just say this. Yeah. Excellent. Again, differentiability implies continuity. Is the reverse true? No. Right? What's your classic example? The absolute value function, right? That's continuous everywhere, but the derivative doesn't exist at the point, right? Because it looks like a v. Okay. So what can we use here if we have a continuous interval like this? Mean value theorem. So by the mean value theorem, we know that we have some number c on that interval. I guess we should probably, I think that's an open interval, such that f of x2 minus f of x1 equals f prime of c times x2 minus x1. What can we say about f prime of c? What do you know about the derivative everywhere? Positive, right? What can I say about x2 minus x1? Remember that x1 is smaller than x2. What does x2 minus x1 have to be?
Positive.
Positive. So what can I say here? Has to be greater than 0. If I add f of x1 to the other side, I have that f of x2 is greater than f of x1. So what does that imply? That f is increasing. And we're done. I just did part A, by the way, in this proof. We're not going to do part B because it's the exact same idea. Right? So what do we say? Or why does this tell us that it's increasing? Well, that's the definition of increasing, right? As you go from left to right, the point should be above the other one, correct? That's all we're saying. All right. So let's do an example then. Let's use this first derivative test, or this increasing decreasing test, excuse me, to find where this function is increasing and decreasing. Cool? Okay. So I'm going to start by taking the derivative. Everybody's cool with that? Note that the derivative or the function here is continuous. How do I know it's continuous? It's a polynomial. I know the derivative is continuous. How do I know that? It's a polynomial. So the only places where a polynomial, a continuous function, can change from increasing to decreasing is at a max or a min, which is going to be where the derivative is either equal to 0 or does not exist, right? So in this case of a polynomial, can the derivative exists everywhere, right? So we don't have to worry about that. We just have to worry about where the derivative is equal to 0. Okay. So we just need to solve this equation. Let's do this without a calculator, because it's certainly doable with what we know to do that without a calculator. How do I solve this? Great, which is 12x. Very good. Okay. Then what do I do? I would factor the quadratic again, right? That should recognize something that's factorable. How does that factor? Plus 1, you mean? That's what you meant. Okay? We got it all the way factored, which is excellent. Now we just apply the zero product property. Divide both sides by 12. Add 2 to both sides. Add 1 to both sides. Or sorry, subtract 1 from both sides. Everybody happy there? So if I think about what's going on, these are the places where the graph can change from increasing to decreasing, correct? So what I'll do is I'll select a test value in each of these 4 places. plug those into the derivative, and see whether it's positive or negative. So from over here, maybe I'll pick -2. Here, maybe we'll pick -1/2. Here, I'd pick 1. And here, maybe I'll pick 3. I said we really need that. Okay. So if I plug -2 in here, I'm going to get -24 times -4 times -1. That is 3 negatives, so it is. So that's negative. Okay. If I plug in -1/2, 12 times -1/2 is negative. -1/2 minus 2 is negative. -1/2 plus 1 is positive. 2 negatives multiplied together is positive. If I plug 1 in, 12 times 1 is 1. 1 minus 2 is negative. 1 plus 1 is positive. I have 1 negative, so that is negative. If I plug 3 in, I have 3 times 12, which is positive. 3 minus 2, which is positive. 3 plus 1, which is positive. 3 positives is positive. So we know that we are increasing from -1 to 0, and then again from 2 to positive infinity. And we're decreasing then from -infinity to -1, and from 0 to 2. So Sergio, I got those numbers. -infinity to -1. This is positive, so it goes from -1 to 0.
Right. No, I was saying like this is random numbers.
I just picked something from the interval.
Okay.
Right, so I needed something between -infinity and -1. I picked -2.
Okay.
Just because it was going to be easy to plug it in.
All right.
Right? I need something between -1 and 0.
I see.
Pick -1/2. Just needed something. Doesn't matter what the number is. Just need something from that interval. Everybody's cool with that? What's the biggest hassle? It's that check at the end, right? Having to do the plugging back into the first derivative and figuring out whether it's positive or negative. Not that big of a hassle, but like that's the hassle. The next piece is called the first derivative test. So it says, suppose C is a critical value or critical number of a continuous function f. If f prime changes from positive to negative at C, then f has a local maximum at C. If f prime changes from negative to positive, that should be a maximum, right? If we change from negative to positive, that should be a minimum. And if it doesn't change, there's not a local maximum in there. So an example might be something that does that, right? Where it just like levels out and then goes up. Like a cubic function. If you look at x cubed, the derivative of x cubed at 0 is 0, but it's increasing on either side. It's not an extreme point. Okay. So if we wanted to go back and find the local, Taylor? Yep. If I wanted to then find the local max and min, let's use that function we just worked on. Let's go back and look at our table and decide whether these are maxes and mins. Okay, so if I look at stuff out of there. So if I look at -1, we go from negative to positive. That is that's a min. If I look at 0, we go from positive to negative. That's a max. And then if I look at 2, we go from negative to positive. That's a minimum. Oops. Pretty easy, right? Once I've done the increasing and decreasing piece, I can get the maxes and mins. They just tumble right out of there for me. No additional extra work for me to do. I just have to analyze the work that I've already done in a little bit different way. Isn't that always nice when it's like, oh, look, the work I did, it got me this other stuff for free, and you don't have to do anything for it. Okay. Let's do a second example here. That's a little bit more complicated because it's not a polynomial. First off, is g of x continuous? You should be able to know just by looking at it. Yes. Why? It's a polynomial plus a trig function. So you have continuous plus continuous is still continuous. Everybody's good with that? Okay. So we're good there. So we'll just take the derivative. So we have the derivative. We need to find the critical values. Worth pointing out, is the derivative continuous? Yes, right? Polynomial plus trig. Well, sine or cosine. Not all trigs are continuous, right? But sine and cosine are. So we're good. There's no place where the derivative doesn't exist. So all we need to do is worry about where it's equal to 0. So I subtract 1 and divide by 2. Then we'll do the cosine inverse to both sides. All right, what values of x between 0 and 2 pi is cosine equal to -1/2? What quadrants are these in? Let's start there. Where is the x coordinate or negative? Remember, cosine is x on the unit circle. Second and third. Okay? Okay. In the second quadrant, then, where is cosine equal to -1/2? So sine would be positive √3/2 in that spot. Ooh, guys. Let's go look at the unit circle real quick. Where did I put? Oh, it's up at the top, right? Where did I put that? Oh, it's here. 2 pi over 3 and, oops, 4 pi over 3. That's okay.
But, like, if it's cosine inverse, like, that doesn't matter.
Cosine inverse is giving you the angle measure back, right? So it's giving us an angle, right? These are angles in radians, right? If I did cosine of 2 pi over 3, it would give me the x-coordinate from the unit circle, which is negative 1/2.
Wait, say that again. If
So like cosine takes an angle to like the x-coordinate on the unit circle. Cosine inverse takes the x-coordinate on the unit circle and sends it back to an angle. Right? So just like, it just reverses the direction for us. Okay. So that's that. So the interval we have to worry about goes from 0, and then we'll have 2 pi over 3, and then we'll have 4 pi over 3, and then we'll have 2 pi at the end. Okay. Let's pick a test value. What's going to be the easiest value to pick between 0 and 2 pi over 3? Pi over 2, yes. Excellent. Why? What's cosine of pi over 2? 0. So 1 plus 2 times 0 is positive. Okay. What are we going to pick here between 2 pi over 3 and 4 pi over 3? Sure, that's fine. I would have picked 3 pi over 2, but that's, oh no, that's after. Never mind. Yeah, pi's great. What is cosine of pi? -1. So 1 plus 2 times -1 is negative. And then what would be a good value to pick over in this spot? I already spoiled it, right? 3 pi over 2. What's cosine of 3 pi over 2? Zero, right? The same as cosine of 90, right? This cosine 270 should be the same as cosine of 90.
We're plugging,
So 1 plus 2 times 0 is positive. And we're doing, yes, we're plugging them into the derivative. Yes, that's what we're doing. Okay, so what do we got here? We go from increasing to decreasing. So 2 pi over 3 is a maximum. And then we go from decreasing to increasing. So 4 pi over 3 should be a local minimum. Everybody cool with what we did there? And again, like, think about it like the first derivative test. Just think about it in your head, like increasing, decreasing, minimum, increasing, like increasing, decreasing, maximum, decreasing, increasing, minimum. Like just visualize it in your head. It makes perfect sense what you're looking at if you just kind of draw the picture in your head. So it should be easy to remember. Second derivative test. Second derivative stuff. So this is what we did is we started with was all things that the first derivative can tell us about f. Now we're going to look at what the second derivative can tell us about f. Everybody's okay with that? So we're going to start with a definition because the main thing that the second derivative is going to tell us about f is going to be what we're going to define right here. So we say if a graph of f of x lies above all of its tangents on an interval I, then is considered concave up on I. If the graph of f lies below all of its tangents on I, is called concave downward on I. So just for like illustration, like that section is concave down. Looks like a parabola opening down. Well, not really that whole section. I'm sorry. It's like from here to here is concave down. Here to here would be like concave up. Here to here is concave down. The way I kind of visualize it in my head is if I dumped water on that section, would the water run down, like run off it like a roof, or would it be caught in it like a cup? Right? This section is concave up. This section, still concave up. And then this last section is concave down. Just trying to give you a visual of what we're talking about between concave up and concave down. So these points here, where the graph changes concavity, we're going to give a special name to in just a moment. Okay. The concavity test. If f prime is positive, or f double prime is positive, excuse me, then we're concave up. And if f double prime is negative, then we're concave down. Everybody's cool with that? So positive concave up, negative concave down. A point on the curve is called an inflection point if f is continuous there and the curve changes from concave up to concave down or from concave down to concave up. So these guys up here we would call inflection points. All the places except at E, right? E is not an inflection point. Everybody's cool? Well, it's concave up and concave up, right? There's no change in concavity. Okay, so let's do an example here. We're going to put together all these things that we've talked about. I'm going to ask to sketch a graph of a function that satisfies the following conditions. That the first derivative is positive on the interval from negative infinity to negative 1. And it's negative on the interval from 1 to infinity. So I'm going to start just kind of sketching some stuff out. Here's my x-axis. So the value 1 is going to matter to me because that's where the graph needs to change from increasing to decreasing at, correct? Everybody's cool with that? Okay. Condition 2 says that the second derivative is positive on the interval from negative infinity to negative 2. So negative 2 is going to matter. And from 2 to positive infinity. but it's negative on the interval from -2 to 2. So what is that saying to us? This was telling us increasing, and this was telling us decreasing. This is telling us concave up, and this is telling us concave down. Mackenzie, you said something, but it kind of mumbled off at the end and I missed it. Yeah, we're going to read that right now. The third condition, the limit as x approaches negative infinity of f of x is -2. And then the limit as x approaches positive infinity is 0. What are those telling us? Those are telling us end behaviors. So the first limit tells us the left end behavior, and the second limit tells us the right end behavior. So let me just draw in a little asymptote here at -2, and another asymptote, well, asymptote-ish anyways, here at 0. I don't think we're going to be able to draw it so that both of those are actually horizontal asymptotes. Okay. So from negative infinity to +1, we're increasing. And at the same time, from negative infinity to -2, we're concave up. So like, we have something like that. And then from -2 to +2, we're concave down. So now we're starting to turn over, but we're still increasing all the way to 1. At that point, we're hitting a maximum. We're changing to decreasing, but we're still concave down. Now we switch back to concave up, still decreasing, but our end behavior has to follow 0 there instead of -2. So we have like an inflection point here, an inflection point here, and a local max here.
Like what points did you use? Like there's so many points of negative infinity to 1. Could you explain?
Well, these aren't points, those are intervals. Right? So that's saying we're on the x-axis. So all the way from negative infinity to 1, my graph needs to be going up, which it is, right? And then it's saying, okay, from 1 to infinity, so this part needs to be going down, which it is, right? So that looks good.
So the first part tells you like what goes up, what goes down.
Yes. So this is just telling, the first condition tells us increasing, decreasing. Let's do the same thing here. For the next piece, from negative infinity to -2, we need to be concave up. So it needs to be like catching water. That looks good. And then from 2 to positive infinity, it needs to look like it's catching water. That looks good. Mackenzie?
Wait, so the inflection points are the ones where it's just concave up to concave down.
Or vice versa, yes. Exactly right. And then from -2 to 2, this spot, we need to be concave down. which we are. That looks like water would run off the roof of that if you dumped water on top of it. Okay. And then the last piece we had was just the end behaviors. So this is just telling us the left arrow needs to be following at -2, and then the right arrow needs to be following along at 0. Paul?
So the second part is finding if it's concave up or concave down.
Correct.
Okay, gotcha.
And the third condition just is telling us the end behavior, what the arrows are doing at the ends of our graph. Taylor?
What are the points called? Where it like switches?
Inflection points is where we change from increasing to decrease, or from concave up to concave down, or vice versa. Mia? Yes. Yes. I just, again, the directions were sketch, so I notice I didn't even really include any y coordinates on my picture other than at -2, because I needed an end behavior there. So I needed to draw that coordinate in, or that tick mark in anyways. You know, there's no reason that, you know, like it couldn't have gone, you know, that you couldn't have done like, you know, like it doesn't matter. You know, it's just a sketch. Okay. The second derivative test is the last idea in this section. So it says that suppose f double prime is continuous near C. So it just means in the neighborhood of C. If f prime is equal to 0 and f double prime is greater than 0, then it's a local minimum at C. And if f prime is equal to 0 and f double prime is negative, then it's a local maximum at C. Is this doing the same thing as the first derivative test? Yes. It's telling you the exact same information, just using a different tool instead of using the increasing decreasing piece to tell if it's a maximum. We're just using the first or the second derivative. So I want to point out to you, this is the drawback, that if the second derivative is equal to 0 at C, then you can't really say anything. What do you do in that case? Have to go back to the first derivative test. Okay, so the second derivative test is quicker. There's less things to compute. The catch is that you might run into a spot where it doesn't work. Now, does that happen often? No, but if it does happen, that's the workaround. Okay. Oh, it's also, yeah. 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 So again, the first derivative test I think is usually the better way to go because there are some catches here, but we'll do this. All right. It says discuss the curve y equals x to the fourth minus 4x cubed with respect to concavity, points of inflection, local maxima, minima, and then use the information to sketch the curve. Okay. First things first, is that continuous? Okay. What's the derivative going to be? 4x to the third minus 12x squared. Is that continuous? Yes. Good. Okay. And then we'll need the second derivative also. That's going to be 12x squared minus 24x.
So what we just did was the first derivative, this is the second. Yes, okay.
I think that's what I labeled, right? It's okay. Let's start by finding the critical values. Now, are there any places where the first derivative will fail to exist? No, because it's continuous, it's a polynomial, right? So they don't have to worry about those. All I have to worry about is when the derivative is equal to 0. I'm going to solve this by factoring. I'll take out a greatest common factor of 4x squared. When I use the zero product property, what are my solutions? You do it in your head. How about 0 and 3? If I set 4x squared equal to 0, I divide by 4, still 0. Square root both sides, still 0. Okay. Let's get the inflection points now. Those happen where the second derivative is 0. Right? The only places where we can change concavity is where the second derivative goes from negative to positive or positive to negative. If it's continuous, which it is, that's just going to be at the zeros. Everybody's happy here? Okay. So let's pick some values. So f prime of negative 1, if I plug negative 1 into 4x squared, that's positive. If I plug negative 1 into x minus 3, that's negative. Positive times negative is negative. If I do the same thing with positive 1, I get positive times negative. That's negative. If I do the same things with 4, I get positive times positive. That's positive. So I see that x equals 3 is a, which one? Local min, thank you. It's not an inflection point because it's not with the second derivative, right? What's x equals 0? It's not a max or a min. It's just like a place where the graph is going to flatten out. Well, it'll be like this because it's decreasing the whole way. Okay, we'll do the same thing over here. So these are our inflection points now. So let's just pick some values. And we'll plug them in. So negative 1, when I plug that into 12x, I get negative. When I plug negative 1 into x minus 2, I get negative. Negative times negative is positive. When I plug 1 into 12x, I get positive. When I plug 1 into x minus 2, I get negative. Positive times negative is negative. I plug 3 into 12x, I get positive. Plug 3 into x minus 2, I get positive. Positive times positive is positive. So each of these are inflection points where the concavity changes. So let's kind of summarize what we have here. We are increasing from 3 to positive infinity. We're decreasing from negative infinity to 0. union 0 to 3. Can't say that we're decreasing all the way through because at one point the slope there is 0. We're concave up from negative infinity to 0, and then from 2 to positive infinity. And then we're concave down from 0 to 2. I have a local minimum at x equals 3, and I have inflection points at x equals 0 and x equals 2. Everybody's okay with the summary we just made here? And then we want to sketch the picture, and that's probably the last thing I have time for. I had one more example, but that's okay that we didn't get to it because it's the same thing.
So it's, the points are 0 and 2 for inflection points because like they change.
Correct, because the concavity changed.
And if they don't change, then
They're
it's
nothing.
not.
They're nothing. So there's 3 points that I need to worry about on my x-axis: 0, 2, and 3. Okay. From negative infinity to 0, we're decreasing and concave up. So we need to be doing like that. And then we stay decreasing, but we change to concave down here. And then we switch back to concave up. Hit our local minimum, so we're decreasing the whole way. So like all that part is going down. And then from 3 to positive infinity, we're increasing and we're concave up. So it should look something like that. And if you wanted to, again, inflection point, local min. Everybody okay on this section? Again, like technically, like this is pretty easy. Like the algebra that you're doing is not difficult. The calculus you're asked to be doing is not difficult. Conceptually, there's a lot of stuff to kind of keep track of and make sure you really understand. But if you understand like what the derivatives are saying, the sketches aren't bad. The tests, what they mean aren't bad. It's all fairly straightforward. There's not a lot tricky going on. The problem set is here at the end. It's also up on the My Notre Dame page. I haven't put the assignment into the calendar yet, I don't think, but it's up there. I don't know. What do you guys... Let's probably put this one into the current problem set, and the next ones will be into the next week's. Probably makes the most sense to spread those out a little bit. That feel fair? Yeah, I think that's okay. Victoria, what's up?